Welcome to The Explainer, where today we're going to crack the code on something kind of weird. It turns out those random numbers that protect, everything about your digital life, they might not be random at all. So let's get right into it. Think about it. When some system needs a random number for security, where does it come from? You probably guess it's tapping into some, truly chaotic, unpredictable force of nature, right? Well, the answer is actually pretty surprising. Most of the time, it comes from a totally predictable, deterministic algorithm. Yeah, you heard that right. The vast majority of random numbers in crypto aren't really random. They're what we call pseudorandom.
Okay, so to really wrap our heads around this, you gotta understand that there are basically two main ways computers cook up these random numbers.
All right, on one hand, you've got what's called a true random number generator, or a TRNG for short. Now, these things are cool. They actually listen to the real world. We're talking chaotic stuff like atmospheric noise or even the tiny jittery movements of your mouse to create bits that are genuinely unpredictable. But then on the other side, and this is the one we see most often, we have pseudorandom number generators, or PRNGs. And these guys, they're just algorithms. They follow a recipe to make a string of numbers that just, looks random. And this is where it gets really interesting. The whole thing hinges on this one little piece of data called the seed. You can think of it like the secret ingredient in a recipe, or maybe the first domino in a huge chain. The moment you give that seed to the PRNG, the entire sequence of numbers it's going to spit out is locked in. It's totally determined from that point on. So right away, that should set off some alarm bells, right? If these algorithms are often public, what happens if a bad guy gets their hands on the seed? Simple. They can reproduce the entire bit stream, every single number. It's like if they knew the first move in a chess game, they could predict the entire match. And in the world of security, that's not just bad, that's game over. A total catastrophic failure. So, okay, how does one of these pseudo-random machines actually work? What's going on under the hood? Let's look at a classic example, a linear congruential generator. Now, don't worry, the formula looks a little intense, but the idea behind it is super simple. Step 1, you start with your seed. Step 2, you run it through that formula. Step 3, the answer you get is your next random number. And then, for step 4, you just take that new number and feed it right back into the formula to get the next one. You just repeat and repeat and repeat. But here's the trick. The real magic isn't the process itself. It's picking the right numbers for that formula. See, if you pick bad numbers, your sequence might start repeating itself way too soon, and that's obviously terrible for security. But if you choose your parameters just right, oh man, the sequence can go on for billions, even trillions of steps before it ever loops back around. It'll look perfectly random to anyone trying to guess. Okay, so we have this predictable but looks random stream of numbers. How in the world do we use that to make something secure? Well, that's where something called a stream cipher comes in. It's a really clever kind of encryption. Instead of encrypting big chunks of data at once, it works on your message one little piece at a time, like one byte after another. And what it does is it takes that stream of pseudorandom numbers, we call that a key stream, and uses it to completely scramble your message. And the process is actually super elegant. It works like this. The PRNG generates one byte of the key stream. Then you take one byte of your actual message, your plain text, and then you combine them using a cool little operation called XOR. What comes out is one byte of your encrypted message, the ciphertext. And you just do that over and over again for your whole message. And here is the beautiful part, the real magic of XOR. It's perfectly reversible. So if you're the person receiving the message, you just take that encrypted ciphertext and you XOR it again with the exact same keystream byte, and poof, out comes the original readable message. It's amazing. All it means is that you and the person you're talking to just need to have the same secret seed to start with. Which, you guessed it, brings us full circle, right back to the single most important part of this whole puzzle, that all-important seed. Now, obviously, the PRNGs we use today are way more sophisticated than that simple example. Their security isn't just about hiding the seed anymore. It's about basing the whole thing on incredibly hard math problems. Like for some of these systems, trying to figure out the seed just by looking at the numbers it produces, well, it would be as hard as trying to find the prime factors of a ridiculously huge number. We're talking a problem that would take our fastest supercomputers literally billions of years to solve. It's just not gonna happen. So here are the key takeaways, right? First, security doesn't actually come from true randomness. It comes from unpredictability.
Second, a PRNG's output is totally predictable if you know the secret ingredients, the algorithm and the seed. Which leads to the big one. That seed has to be a secret, and it has to be unpredictable itself. And how do we do that? Well, in a beautiful little twist, we often use a true random number generator to create the seed for our pseudo-random number generator.
So let me leave you with this question. If the algorithm is public knowledge and the process is totally predictable, what's the real secret we're protecting? It's not some magical chaos. It's just a single number, a tiny, well-hidden, unpredictable starting point, a predictable secret that our entire digital world is built on.